Hello everyone, I am Dr. Sirajul Faizi. I welcome you in my YouTube channel. Today in this video, I am going to talk about elimination reactions. So what is elimination reactions? You know my friends, elimination reactions are those reactions in which hydrogen atom along with a living group will be eliminated. Living groups like iodine, bromine, chlorine, OTS, OMS, OBS, like this. The second important point related to elimination reactions is elimination reactions widely used for the generations of double and triple bonds in compounds from a saturated precursor molecules. The next important point related to elimination reactions is the presence of a good living group is prerequisite in most elimination reactions. And then the important point is based on position of elimination group or eliminating groups. Again, these reactions are classified as alpha eliminations and beta eliminations. So first I will discuss about alpha eliminations. You know the reactions in which both the group, that is hydrogens and living groups, departs from the same carbon atoms. Such reactions are called alpha eliminations. For example, generation of carbene intermediate in Riemann-Tiemann reactions and cyclopropanation Siemens-Smith reaction. So you can see here the reactions. This reaction is going through the alpha elimination. So you have bromo form, CHBr3 is bromo form. You have potassium hydroxide, it gives this carbene CBr3 and K plus. And further this compound eliminate this Br and forming dibromocarbene. So in the presence of a base, chloroform or bromoform or iodoform can be dehydrohalogenated. Dehydrohalogenated means removal of halogens and water to form a carbene. So now beta eliminations. What is beta eliminations? The reactions in which if hydrogen atoms and living groups are eliminated or departed from the adjacent carbon atoms, such reactions are called beta elimination reaction. And thus these reactions are highly utilized in organic chemistry for generations of multiple bonds from alkyl halides. For examples, when alkyl halides undergoes an elimination reaction, the halogen is removed from one carbon and proton is removed from an adjacent carbon. Just as there are two mechanisms of substitution, SN2 and SN1, there are two mechanisms of elimination, E2 and E1. E2 mechanism, bimolecular elimination, E1 mechanism, unimolecular reaction. The E2 and E1 mechanism differ in the timing of the bond cleavage and bond formations, analogous to the SN1, SN2, you know that. Now, E2 and SN2 reactions have some features in common and do E1 and SN reactions. You know, base removes a proton from beta carbon. You can see the beta carbon. This is the alpha carbon. While the halogen atoms leave from the alpha carbon, resulting in the formation of a pi bond, and such elimination are called beta elimination reactions. Now, E2 reactions. Just as there are two important nucleophilic substitution reactions, SN1 and SN2, there are two important elimination reactions, E1 and E2. The reaction of tert butyl bromide with hydroxide ion is an example of E2 reaction. E stands for elimination and 2 stands for bimolecular. The product of an elimination reaction is an alkene. The rate of an E2 reaction depends on the concentration of both butyl bromide and hydroxide ion. It is therefore a second order reaction. So rate is equal to K, concentration of alkyl halide and concentration of base. The rate law tells us that both tert-butyl bromide and hydroxide ion are involved in the rate determining steps of the reaction, and the following mechanism agrees with the observed second order kinetics. So mechanism of the E2 reactions is like that. You can see this proton is removed by this base and this bond shift here, and meanwhile breaking of this Br is eliminated. So formation of double bond. So you can see here the E2 reaction is consorted, one step reaction. The proton and bromide ion are removed in the same step, so no intermediate form. Now you can see this base is trapping this hydrogen. This is beta carbon, this is alpha, and removing Br from the alpha carbon. So energy profile for an E2 reactions is like this. This profile is energy versus reaction coordinates. Reaction coordinate is in this directions and energy in this direction. So more stable compound is this, and more energetic compound is transition state. So in a series of alkyl halide with the same alkyl group, alkyl halide are the most readily active and alkyl fluoride and least reactive in E2 reactions because weaker bases are better leaving group. So relative reactivities of alkyl halide in an E2 reaction is like that: most reactive Ri greater than Rbr greater than Rcl and least reactive Rf. Now reduced selectivity of E2 reactions. E2 reactions are reduced selective and favor the formation of jet-safe products. You can see this is the 3-degree carbon and formation of this product. These two products, one is minor and another is major. What is the reason behind it? An alkyl halide such as 2-bromopropane has 2 beta carbon from which a proton can be removed in an E2 reaction. Because the 2 beta carbon are identical, the proton can be removed with the equal easy from the either one. The product of this elimination reaction is propene. So you can see the beta carbons, you can see the formation of propene. If you have beta carbon is like that, 2 bromobutanes. So in presence of methoxide, it gives 80% 2-butanol, 20% 1-butene and methanol and Br. So transition state leading to 2-butene, which is more stable, and transition state leading to 1-butene, less stable. So that this is the reasons the product and yield of the reactions of 2-butene is 80% and this one is only 20%. Now the reaction of 2-bromo-2-methyl-butene with hydroxide ion produces both 2-methyl-2-butene and 2-methyl-1-butene because 2-methyl-2-butene is the more substituted alkanes. It has a greater number of alkyl substituents bonded to its sp2 carbon. It is the more stable of the two alkenes and therefore is the major product of elimination reaction. So 2-bromo-2-methyl-butene in presence of OH minus, it gives 70% 2-methyl-2-butene and only 30% 2-methyl-1-butene. Now Alexander Zhestsev, in 19th century Russian chemist, devised a shortcut to predict the more substituted alkene product. He pointed out that the more substituted alkene product is obtained when proton is removed from the carbon that is bonded to the fewest hydrogen, and this is called Zhestsev rule. In 2-chloropentane, for example, one carbon is bonded to 3 hydrogens and other carbon is bonded to 2 hydrogens. According to Zhestsev rule, the more substituted alkene will be the one formed by removing a proton from the carbon and that is bonded to 2 hydrogens rather than from the carbon that is bonded to 3 hydrogens. So you can see here 2-chloropentane. So 3 beta hydrogens, here 2 beta hydrogens. So this CH2 and CH3 is disubstituted. So 67% mixed of the E and Z. Here is these all are monosubstituted, 120, 33%. Now we understand what is the fewest hydrogens. Now, relative reactivity of alkyl halide in an E2 reaction, tertiary alkyl halide is greater than secondary alkyl halide and greater than primary alkyl halide. So 3 alkyl substituents, 2 alkyl substituents and 1 alkyl substituents. Here 1, here 2, here 3. The increasing in E2 reaction rate with increasing alkyl substituent can be rationalized in the term of transition state stability. So 4-chloro-5-methyl-1-hexene give major products and minor product. Here the double bond is conjugated with the benzene rings. Here the double bond is not conjugated with the benzene. So this product is 28%, this is 72%. Approach to the hydrogen is strictly hindered here and bulky groups, bulky base. Then in case you will get the in opposite result 72% to methyl 1-butene 28%. Now you can see the effect of steric properties of base on the distribution of product in an E2 reaction. So if you have this base, simple base, more substituted base and bulkier base. So this one is giving more substituted product 79 and less substituted 21%. In case if you have the bulky base, then 92% less substituted, opposite, and only 8%. So this table is very important for NET examination. When a sterically hindered alkyl halide undergo an E2 reaction with a variety of alkoxide ion, the percentage of the less substituted alkene increases as the size of the difference. If the alkyl halide is not strictly hindered, the base only moderate hindered, the major product will still be the more stable product. Now, dehydrohalogenation of cis 1-chloro-2-methyl-cyclohexene. So, in this conformer, 2 hydrogens are anti-periplanar to Cl. So, you can see the Cl, these 2 hydrogens are anti-periplanar. And in this conformation, C1 is an equatorial position and has no hydrogen periplanar groups. So, the conformer with Cl is an axial orientation react to give 2 alkene. The alkene is more substituted is major products. So you can see disubstituted alkenes minor products and trisubstituted alkenes major product. So this is the major product and this is the minor product. Very important for NET examinations. Now dehydrohalogenation of trans 1-chloro-2-methyl-cyclohexene. So in this conformation, C1 is an equatorial position and has no hydrogen periplanar to it. In this conformation, 1 hydrogen and 1 CH3 are anti-periplanar to the Cl. So the conformers with Cl is an axial orientation has just 1 beta hydrogens. You can see here. Only 1 product is formed, which is not what is the predicted by Jetsev rule. So disubstituted alkene the only product formed. So in conclusion, with the substituted cyclohexane, E2 elimination should occur with a transdiaxial arrangement of the leaving group and the BH beta hydrogen is the result of this requirement. The more substituted alkene is not necessarily the major product. So my friends, I hope this video will be helpful to you. If you like this video, then subscribe my channel and thanks for watching.